he's related to the Prince's School of Traditional Arts in UK, and he will be talking about geometric patterns based on grids. Amit, everything is yours.
Thank you. Hello, everyone. First of all, I'd like to just thank Mirek and the Istanbul Design Center for inviting me again and to be able to visit this beautiful city. So this is the topic of my talk, particularly focusing on square and isometric grids. When I say isometric, just so everyone knows, I'm talking about triangular grids. These two are some of the most obvious and flexible grids to base geometric designs on. And the reason for this is because they arise from the simplest tilings of the 2D plane. So there are only 3 regular polygons which can tile a 2-dimensional plane by themselves. First of all, we have the triangle. Closely related to that, we have the hexagon. And finally, the square. So the triangle and hexagon are basically the same thing in terms of a grid system. So before we look at the patterns themselves, I wanted to discuss the construction of them by hand. Now, obviously, these days we can go to a website, download a grid in any size we want, whether it's square or isometric, print it out, or use any other digital method to do that. Doing that, however, misses an opportunity to understand why these grids have unfolded from the circle mainly. So first of all, we have the 6-fold division. So the circle divides itself naturally into 6. You can see 6 circles of the same size fitting around. If we join the tips of the petals, we get a hexagon. And joining points across the hexagon divides it into 6 triangles. So I'm going to present a couple of ways that you could construct these by hand and discuss the merits of each. So here we have what's often called the flower of life or creation pattern. And it's based on the idea of the circle dividing itself into 6. This process, as you can see, is something you can extend outwards indefinitely. It makes a very beautiful design in itself and is very satisfying to see it unfold as an act of drawing. However, it's not a very practical and accurate method for the reason that we're starting with something small and moving outwards. We also don't have any control over the size of the final grid, apart from the initial circle. So the inaccuracies, by starting small and working outwards, can compound. So if we then connect up across the tips of the petals, we can define our isometric grid. So a very beautiful way of drawing it, but prone to inaccuracies. The second method starts with the outside circle, which we divide into 6. Connecting those points gives us our hexagon. And then we subdivide from there. We already have one set of triangles. And we carry out a process of connecting different points in order to construct smaller triangular grids. So the previous method, we're working in to out, and in this method, we're working out to in. This method is much more accurate, starting with the large circle and working inwards, less prone to inaccuracy. We're also working within a fixed area instead of expanding outwards and not knowing where we'll end up. Okay, so the square grid. So from the fourfold division of the circle, we can apply a similar procedure, placing circles on the four corners, connecting the tips of the petals to define a square. Now again, we can take a similar approach, starting with a small circle working outwards, as you will see here, to define a square grid. So although these methods, this one and the first method from the hexagonal design, are not necessarily the most practical, they are very beautiful, and they help us to understand why and how these grids have become such a fundamental feature of geometric design. So again, second method involves starting with a square. Now again, this time we're drawing a circle first, which has the same diameter as the square that we're going to... Sorry. So we divide the circle into four. Then we can mark the corners and define our first square. So the square is, we can use the diameter of the first circle to be the width of the square. And then we start the subdivision process. Again, we're subdividing theoretically infinitely inwards. Obviously, in practice, we're not going to be able to do it infinitely. But we place diagonals into each square, and that allows us to generate a further subdivided grid. Now, what's particularly interesting here is that the interplay between the two grids, the dynamic and the static, so the static being the horizontal square grid, the dynamic being the one on its points, those two grids interact with each other, as we'll see in some of the designs later on, in a very effective way. A couple of other possibilities for constructing would be to use a set square. The two most common set squares are one with two 45-degree angles and a 90, or a 60, 30, and 90, and those two can be used to draw grids as well. And in order to transfer this to a new sheet of paper, if you're working entirely by hand, you can lay your grid onto a sheet of paper and prick holes through so that the piece you're working on just has holes marked in a network of dots that define the grid. So we'll see now how these grids can provide a valuable and effective generative system for pattern design. So we're going to start by looking at isometric grid. Here we have a very effective standard honeycomb tiling being used as the design itself. And here we have hexagons tip to tip instead of edge to edge, and this creates triangular spaces in between. Now these two approaches, edge to edge tiling and tip to tip tiling, is something we can carry through all the explorations. Okay, so the hexagon is a very simple unit to tile. However, in a practical sense, especially if you're talking about architectural context or the book arts, pages, sides of buildings are rectangular. So what's often a much more useful compositional method is to define a rectangle within the hexagon, and the proportions of the sides, as you can see, are 1 to √3. So this is often referred to as the √3 rectangle. So our first pattern, before we actually look at the grid itself, just wanted to point out the relationship between the triangular and hexagonal grids. So the hexagonal and triangular grids are what you could call duals of each other. So looking at the two overlaid, you can either see it as 3 hexagons on the tips of the triangle or 6 triangles on the tips of the hexagon. And from this, we can define our first pattern. This is entirely made of one kite shape, so a single tile. Okay, so from the flower of life, of creation pattern, we define our isometric. So it's very easy to draw designs on isometric grids just by connecting the points, connecting the intersections. But in order to create a successful repeat pattern, we need to understand something about a tiling unit. So I'm going to look at a few different ways to sequentially explore repeat patterns using this system. But the possibilities are vast, and so we're only really going to skim the surface today, but you'll hopefully see how it's very flexible. So the first, most common pattern is defined by drawing a 6-pointed star within a hexagon tile and expanding outwards. And here we have possibly the most common, or one of the most common Islamic star patterns seen in many, many different places and in different media and different contexts. And it could almost be seen as a kind of prototype for all Islamic star patterns in the sense that we have star motifs touching each other tip to tip. Here's a particularly beautiful carved stone screen example. And this example from Itimad ad-Dawla shows the pattern has this dual level quality, something which is relatively underexplored within six-fold symmetry, but used to good effect here. Okay, so the next step in our exploration is to increase the size of the tile. The star size is the same. The tiling unit has been expanded by 1 unit, and the relevant lines have been extended from the star. We extend this out to get a different star and hexagon pattern. And this one can be seen here in Istanbul on the floor of the Sultanahmet Mosque. This example from Cairo in the top 2 windows shows both the patterns we've looked at and suggests that maybe the designers were actually exploring in a similar sequential manner. Okay, we extend the tiling unit out 1 step further, and we can derive this pattern. So now we're going to take a slightly different approach. Instead of the tips of the star touching the edge of the tiles, they're now in the corner of the tile. And this can be extended to give us this pattern, made from just a rhombus, which we'll see cropping up a few times, and the star. And a lovely example of that one. We can derive yet another pattern by putting another 6-pointed star within each of the original 6-pointed stars, and we see the kite shape that we had from the first pattern. Okay, extending the unit out a little further, Gives us a variation on the star and hexagon pattern, which has triangles added within. And again, the tiling unit extended further, and we get this pattern. So you can see now that we are starting to develop a kind of vocabulary of shapes. The star, the hexagon, the triangle, the rhombus, and a few others. And this can provide another basis for exploring these types of patterns by piecing these together in a sort of like a jigsaw. Here's a particularly beautiful example of that design. So a kind of different way of looking at the same, we're using the same grid and we're taking a similar systematic approach. But this time we're going to start with a standard hexagon tiling. And by expanding those hexagons, so it's a sequence of overlapping hexagons. When we hit the next unit on the grid, we can use that to define another very common pattern, just made from hexagons, 2 different sizes. And then if we extend, keep expanding those hexagons, in fact, there we hit a point where we get the familiar hexagon and triangle tiling, and we keep extending further till we get to the next unit. And this gives us yet another design. And if we place hexagons into the open spaces, we've arrived back at the Sultan Ahmet pattern, but from a different viewpoint. Okay, so taking that same double hexagon design and expanding the tiling unit, we get this design. Now here again, in this lower section here on the left and the right, you can see the 2 versions of the hexagon, the double hexagon pattern, the standard one and the expanded one. And again, it gives some suggestion of a narrative in the architectural work. The designers were exploring a system and exploring it in a sequential way and then using those designs in one building. So just a little animation to convey what I'm talking about. You'll see nearly all the patterns we've discussed at different points. And all of this arising just from a grid of hexagons expanding. This is another way of looking at it. Hexagons, static and dynamic, expanding outwards and giving rise to a whole range of possibilities. And all of these arise from that standard triangular isometric grid. Okay, so we're going to take a different way of looking at the grid. Based on rotational symmetry, so rotating patterns. So we design again a tiling unit, this time with the same star at the center, but with rotating elements around it. We can expand that outwards to create this particularly wonderful design from Itimad Ad-Dawla. Again, another 3-fold motif, rotating and expanding outwards. You can see these types of patterns have quite a different feel to the first ones we were looking at. Okay, so this is an unusual one, a bit more interesting. So starting with this layout of nested hexagons, we can generate first that element and then rotating 3-fold shapes. and we can tile that outwards like this. Now, what's particularly interesting about this is that the easiest way to see a repeating unit in it is to connect the centers of the hexagons. But you'll notice that the line connecting the centers doesn't follow the isometric grid. So this is the kind of design that would be very difficult to construct with ruler and compass. But as you can see here, from an isometric grid, it's a very straightforward procedure. So it's a slightly more complicated example. This one combines a very strong isometric pattern with a standard rosette. So just to break this down a bit further, we have two interlocking elements which make up a repeatable hexagonal unit. And then we have the outer structure of a rosette. Now, this is an approximation. So as we move to an actual rosette, there has to be a bit of adjustment. But in the context of the whole pattern, it works. So the rosette is actually what's called a canonical rosette, standard proportional rosette. But the way it connects with the outer shapes is slightly altered. So looking at the whole panel, we have the familiar star and hexagon design, and this forms the underlying structure where the hexagonal units are in place, and inside the six-pointed star we have the rosette. So the grid doesn't restrict us to only using that. It's something that can be quite flexible and used in combination with other design elements and other motifs. Another thing we can do with the isometric grid is actually use a unit width as a band. So if we start with that hexagon, put 6 overlapping ones around it, we can use that to create this interlocking design. And if we take a slightly larger banded unit and apply the same process, we get yet another possibility. So looking at those two in relation to each other, the first hexagon and the second hexagon, the layout of the first pattern and the layout of the second. So I'm only showing two examples here, but that animation showing the expanding hexagons, we could apply a similar process here with these banded hexagons and create a whole new set of patterns from there. Okay, before we move on to the square grid, just wanted to show a particularly familiar and beautiful design from the Alhambra Palace, which actually uses the creation diagram rather than the isometric grid. So this little threefold motif is defined entirely from the curves of the grid and gives us this design, which no doubt you've all seen many times. A last image I wanted to show, this is one of mine which explores the idea of scaling within these types of patterns. So this is actually one pattern which has been overlaid a number of times, at each time scaled at the square root of 3 to the previous layer. And that brings up some interesting connections and possibilities. Okay, so square grids are possibly even more, have even more potential than the isometric ones. As you can see here, the grid can be used to good effect with color just by itself, especially in this dynamic orientation. So given the time restraints and the vast possibilities on offer with these grids, I'm going to concentrate on just a couple of avenues of exploration. So we have our main square grid, and faintly within that we have a dual grid, which is also a square grid, but it's a dynamic one with using diagonals. And we can use this to subdivide the grid further and put in further diagonals. So we're going to use all of these in different contexts within the patterns coming up. But before we look at the patterns, again, just the proportions inherent within the square. So if the side of a square is 1 unit, the diagonal is the square root of 2. We can also swing that diagonal round to generate another very useful proportional rectangle, often called the root 2 rectangle. Okay, so the patterns we're going to look at in this little sequence all take a similar approach. They start with a rotating motif, then they are reflected to create a tiling unit that can be repeated by translation, i.e. sliding along, sliding downwards to create this design. So again, we're starting with a pattern that only uses one piece, a single pentagon. So this is one of my favorite designs, open to a lot of interesting ideas. There are actually a number of different solutions to this one, as in different angles can be used and have been used historically as well. This version is the one that can be easily drawn on a square grid. So we take that motif, again, flip it 4 times, 3 times to generate a tile and extend that outwards. Now the interesting thing about this particular, the proportions used here, is that every length in it is equal. So the square has 1 unit side, and the kite, the short side is 1 unit, the long side is 2 units, and it's divided by the square. So all those lengths being equal give it a very interesting rhythmic. Proportions inherent within the square. So if the side of a square is 1 unit, the diagonal is the square root of 2. We can also swing that diagonal round to generate another very useful proportional rectangle, often called the root 2 rectangle. Okay, so the patterns we're going to look at in this little sequence all take a similar approach. They start with a rotating motif, then they are reflected to create a tiling unit that can be repeated by translation, i.e. sliding along, sliding downwards to create this design. So again, we're starting with a pattern that only uses one piece, a single pentagon. So this is one of my favorite designs, open to a lot of interesting ideas. There are actually a number of different solutions to this one, as in different angles can be used and have been used historically as well. This version is the one that can be easily drawn on a square grid. So we take that motif, again, flip it 4 times, 3 times to generate a tile and extend that outwards. Now the interesting thing about this particular, the proportions used here, is that every length in it is equal. So the square has 1 unit side, and the kite, the short side is 1 unit, the long side is 2 units, and it's divided by the square. So all those lengths being equal give it a very interesting rhythmic quality. As shown here. Okay, so here again we start with what is often called a swastika motif. Obviously that term has very negative connotations these days, but it's a very familiar and widely used approach. And we connect up various other points on there, and we define another common pattern called the fig leaf pattern. Now, because we're using a square grid, it doesn't precisely relate to the 8-pointed star, but you can see that it's a very close approximation. And here we have an extended version from a fountain in Fez. Okay, another common design. Not sure what it's called. I call it the Stingray. And we can, if we halve the size of the design, we can fit it in exactly the same rectangle. Again, another stunning carved screen, carved stone screen. Okay, familiar motif again. Again, placed rotating around, extending into this. Now this makes a particularly good weaving pattern with the grid underneath as well, with a lot of oscillating kind of effect, and works well with color and shading. So a particular aspect of ornamental design which the square grid has provided very fruitful possibilities is the idea of creating borders, ornamental borders. And again, we can use dynamic squares. So all these designs use a combination of the static and dynamic grids, the dual grids. And these can be extended to become ever more elaborate. And it leads us to, I don't know whether this is really a family of patterns, but it's patterns that take a similar approach in the way that they're constructed. So again, they're using the main grid and the diagonals. And by widening the channels and interlacing them, we can derive a repeating border pattern. So that leads me on to the final design I wanted to look at. So there's many possibilities within that. I'm just showing that border to lead on to this one from the Alhambra Palace as well. Again, the basic structure can be drawn on a square grid. And we can see that there are a number of continuous lines which, when the design is woven, turn into an interlocked pattern. So here I've just rendered it in one color. And this is a hand-drawn version. Again, so just to demonstrate how easy with a square grid that these kinds of designs can be to explore. And a couple more examples, again, from the Alhambra. Alhambra is a place where there is certainly a strong narrative in the designs. A lot of similar themes are explored, and this approach is certainly one of them. And a lovely stained glass ceiling. So, as I hope you can now see, there is huge and flexible potential for the use of these foundational grids. They provide a rich and expansive system for design of geometric patterns. There's countless further designs related to the ones I've shown, and countless more that have yet to be discovered as well. And another area, it's actually very useful in a lot of different contexts, paper folding being one, which we're hopefully going to explore with Eric later this week. So I'm just going to leave you with a final animated experiment which shows, again, what happens with expanding squares. Obviously, the static two-dimensional designs are all very beautiful, but there's something, for me, that comes across in the animation of just a simple grid of squares and the possibilities that kind of arise out of that, and seeing it in movement, that really clarifies how flexible these systems are. And finally, just one with half squares that does something very different. So thank you very much for your attention.